class. We're really very pleased today to have Dr. Lineweaver with us. He's the coordinator of the Australian National University's Planetary Science Institute and holds an appointment as Associate Professor in the Research School of Astronomy and Astrophysics, as well as the Research School of Earth Sciences. I'm told he got his undergraduate degree in English literature?
History.
History. Very good.
Graduate degree.
A graduate degree in English and his doctorate in astrophysics from the University of California at Berkeley. Dr. Lineweaver conducts research in the fields of cosmology and exoplanetology, which is the statistical analysis of planets outside the solar system, and in the field of astrobiology. I also understand that he was a semi-professional football player in Germany. So you can do a lot with your life. He's written some 50 articles in scientific journals, 8 book chapters, as well as several magazine articles. I'll read you just a couple of the titles. A Larger Estimate of the Entropy of the Universe, Life, Gravity, and the Second Law of Thermodynamics, Cosmobiology, Our Place in the Universe, and Does the Universe Contain an Infinite Number of Kevin Rudds? Tomorrow, Tuesday, at 3:30, Dr. Lineweaver will be giving a public lecture titled, Are We Alone? At the Rector's Lecture Hall. You're all invited and hope to see you there.
Thank you very much. Can you hear me back there? All right, good. Yes, I've been told that I'm the only cosmologist or the only scientist that gives a lecture in this class, and so I guess I feel there's a burden on me to introduce you to some concepts in cosmology and science. And I'll be talking to you today about, I'll be trying to answer these questions. What is a universe? How big is the universe? How did the universe begin? How old is the universe, and what is the universe made of? I thought that in answering these questions that you would have a beginning to understand where you are. So about 10,000 years ago or earlier, every human being on this planet was in a tribe who had a tribal region. Well, here's Italy, for example, and here are the ancient languages of Italy before it became a nation state. And you can see there's a small region here, a small region here. So if you belong to this particular tribe, this would be your horizon. You could walk in a few days across it. And this is the same thing, but for a piece of Victoria in Australia. These are Aboriginal languages. The point I'm trying to make here is that about 10,000 years ago, 20,000, 100,000, 200,000, human beings had a sense of their world that was about as far as you could walk in a few days. And that's what you can see by these linguistic regions. I should also say that if you have any questions, just raise your hand or call out. That's what I did when I was your age, so I figure I should extend that courtesy to you. And if you don't ask questions, I'll ask my own questions, and then, I don't know, we'll see how that works. So are you used to answering questions? I've been told that you're not used to asking questions, so please feel free. Questions like, how do you know that? Why do you believe that? I don't believe that. And then we can talk about it. So this, by the way, is the other part of cosmology, and that is not, I was talking about these regions of the Earth, but also people used to look up at the sky. When they looked up at the sky, they saw stars, and they invented constellations. This is the Egyptian version of the sky. This is the goddess Nut. And I think her husband was separated from her husband down here, and that's how the sky and the earth were created, according to one version of Egyptian mythology. So, where are we? Here's a Greek map of the universe from 400 BC. And you can see that, like all peoples, Greeks put themselves in the center of the map. And then around it, where they didn't know anything, they put an ocean. Sometimes you'll see, here be dragons. And you can see in many of these maps that where we are is right in the middle of this. So here's a further map from 200 AD, Ptolemy's map. And you notice that the universe got a lot bigger here. And again, I find this interesting. I think maybe they had this original schema for having a map, and then they found out more about here, and then they extended the map into this region here. And these are the winds that are blowing from different sides. Now here's an interesting map. This map was taken, it was used by Bogazici in 1768 as he traveled around the world trying to discover something. And notice that I live, by the way, I live in Canberra, Australia, which is right here. And you can see that that's not even on the map in 1768. Now here's a map of the world, and here's where we are. Right there, you are here. But here's another map of the world, and again, you are here. This is a map of the world at night. These are lights you're seeing. And here's a backup. If we back up a little bit further, this is what the world looks like. And so you can see we've made some progress from 400 to 200 to today, but this is only for the Earth. If we back up a little further, this is what the Earth looks like from the moon. We can back up further, and, well, there we are. Actually, that's where Australia is. If we back up further, this is what the world looks like. This is the moon. This is the Earth. This is a photograph. This is not a drawing. And it takes light. Light travels at 300,000 kilometers per second. The distance here is 400,000 kilometers. So if Houston says, "Hello, Neil," Neil hears it and says, "Hello, Houston, this is Tranquility Bay." Tranquility Bay. That's how fast light travels across the universe. And that is our moon. Now you are here. Now if we back up a little bit further, this is what it looks like, the same thing, the Earth and the moon. We back up a little bit further. This picture was taken by the Voyager spacecraft. No picture has ever been taken from further away. That is a pale blue dot. That is what the Earth looks like from far away from the Voyager spacecraft. We can back up further. And here are the nearest stars to the sun. Here's the sun, and in that yellow dot somewhere is the Earth. And then here are the other stars. The nearest star to the sun is Proxima Centauri. It's part of the Alpha Centauri system. It's 4.3 light years away. The moon is about a light second away, and these stars are about 4 light years away. Now, notice the scale here is 10 light years, and this is 4 light years. Proxima Centauri you cannot see from the northern hemisphere. You have to go to the southern hemisphere to see it. Now, we can go back a little bit bigger and say, now here's 100 light years. And then we can see the few dozen stars, up to 100 stars, that are within 100 light years of the Earth and the Sun. The galactic center is down here. That's the galactic center in this direction. We can go out further, and we see a bunch of stars like this. These are some of the stars in the galaxy. And for example, we could say, oh, you are here. Now, you should recognize that no picture has ever been taken of the sun from this far away. And so, this is illegitimate in some sense. I can't say you are here because no spacecraft has ever looked back at the sun from this far away. If we go further away, this is what it looks like, our galaxy. And we are about there. We're about 30,000 light years from the center of the galaxy. There's a black hole at the center of the galaxy. That's 3 million solar masses right there. And all the stars are going around it. And here is a tiny, tiny fraction of the universe looked at with the Hubble Space Telescope. So if you put your finger like this, the size of this image is about the size of your fingernail. So it's a very, very tiny, tiny fraction of the universe. But you can see all of these dots are galaxies, with several exceptions. So when I say you are here, our galaxy, from very far away, would look like this. But there's a star in our own galaxy, a star in our own galaxy, another star in our own galaxy. But every other spot there is a galaxy. I should say that in our galaxy, there are about 300 billion stars, 3 times 10 to the 11 stars. And in the observable universe, there are about 100 billion galaxies. Does anybody want to know how we know that? Or are you just taking this on my, you say, hey, he's a scientist, he knows what he's talking about. Is that, anybody want to know how we know this, or are you just going to accept this? What's that? By observing light, by having a telescope. Now, but notice that this is a tiny, tiny fraction of the sky. Essentially, you say, okay, I'm going to look at 1/1,000,000th of the sky. And I look at 1/1,000,000th, and I count them, and then I multiply that number by 1,000,000, is basically how that works. So 100 billion galaxies in the observable universe. That's different from the entire universe. This is just the part that we can observe. So you are here. Now, in 1929, this scientist here, who is smoking a pipe, you're not supposed to smoke a pipe in an observatory anymore. And in fact, astronomers do not look through telescopes anymore. They look at computer screens. But in 1929, astronomers still did look through telescopes. And what he found was that these dots are, in fact, galaxies. They used to be called island universes. As a matter of fact, they used to be called nebula. And then he realized those nebula are not in our galaxy. They're very, very far away. And then he noticed something very interesting, that these galaxies were moving away. Now, I think there's a Formula One car race in Istanbul next week, right?
Yep.
Now, if you go to those car races, you'll hear a car go, meow, meow. When it's going, that's when it's approaching you, and the frequency is very high. And then when it leaves, that's the low one. So the frequency increases when it's coming towards you, decreases when it's moving away. That's called the Doppler Effect. And when you look at all these galaxies, they're going, that means they're receding. They're moving away. And we see that not with our ears, but we see it in the spectra of the galaxies. Because the spectra have lines in them from hydrogen and helium and lithium, beryllium, boron, carbon, nitrogen. All of these atoms that are in the atmospheres of the stars produce lines. And the lines are shifted. They're red shifted. That's the blue shifted. This is the blue shifted, these are the red shifted, and all of those galaxies are red shifted, which means that they're receding just like those cars that are receding. But in every direction, they're receding, 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 receding. And when you have all these galaxies receding, that means the universe is expanding. Some people think, oh, that means all the galaxies are receding from us. But in fact, that's not the case. We're not the center of the universe. In fact, the universe itself is expanding. And that's how we understand the expansion of the universe. It's very different from blowing up a bomb. And what's that?
How can you work that it's expanding? We cannot reach maybe we say it's expanding because we can never reach the end of it.
Okay, well, no, that would be infinite. So the question is, how do we know it's expanding? And the answer to that question is, imagine if you had your eyes closed and you heard racing cars. And the racing cars were not going, they were going, They were all receding from you. They were Doppler shifted. So instead, and in every direction, they had this low frequency, which told you they were receding. Another way would be, imagine if I don't know, if you had a purse or a wallet in your pocket, and someone took your wallet, and then you don't know where they went, but then you see the thief running away with your wallet in this direction. Or you can see somebody running away here, running away here. We can see them receding because of the shift in the spectrum of the lines. It's called the red shift. That's how we know. It's like listening to cars going instead of. If we look at these galaxies and saw they're all, that would be blue shifted. They'll all be coming towards us. But we know that they're red shifted, and that's the evidence for the expansion of the universe. And this was found in 1929 by Edward Hubble. Does that answer your question? A little bit. Okay. We can talk later about it. Any other questions about this? The bottom line is the universe is expanding, and you should know this. This is one of the facts about the universe that every human being on this planet should know. Your grandparents, your great-grandparents did not know this because it wasn't discovered, but you should know this. Question?
What is the role of cosmological constants?
Speak it up louder, please.
What is the role of cosmological?
What's the role of the cosmological constant? We'll be getting to that towards the end of the lecture. Basically, the cosmological constant makes the universe accelerate. Not only is the universe expanding, but 10 years ago, we discovered that the expansion was getting faster. It's like these racing cars that are going away, they're not just moving away, they're moving away faster and faster. You got the pedal on the gas. They're really moving away. And that's what the cosmological constant does. And I'll talk about that in a little bit. Any other questions? Does everybody believe that the universe is expanding? Who does not believe that the universe is expanding? Who does not accept this? That's crazy. I don't agree with any explanation you gave. So raise your hand if you think that the universe is not expanding. Is this the first time you've heard about the universe expanding? You in the red shirt. Have you ever heard of the universe expanding? Yes. You've heard about this before? So you accept it? You say, sure, if you say so. Okay, so this is not new. Okay, so you can accept it. Okay. Anybody else? Anyway, if you want to know more about any subject, just Google, Wikipedia, expanding universe. Yes. Where does the universe expand? That's a very good question. So everything you're used to, everything that expands, like a balloon or a bomb, expands into something, right? The universe is not expanding into empty space. This is probably the weirdest and hardest thing to understand about general relativity. The universe is not expanding into previously empty space. But the best way, one way to understand this is consider an infinite trampoline. Do you know what a trampoline is? Consider an infinite trampoline. It goes on forever in all directions. And then make it bigger. So it's not expanding into anything. One example of an expanding universe, you take a balloon, a rubber balloon, and you put dots on it. And you go, and you blow it up like this. And the distances between each of those galaxies gets bigger and bigger and bigger, no matter where you are. But the problem is that the balloon is expanding in space because it's surrounded by space and it's getting bigger and bigger in the space. And that is not the kind of expansion that the universe is going through. Now, I know that's hard to believe, and it's difficult because you have never seen anything like this, but that's what Einstein's general relativity tells us. The universe is expanding without needing anything to expand into. So the answer to your question is, it doesn't expand into anything. It just expands. And you're going to say, that's crazy. That makes no sense. I've never heard of anything like that. And you'd be right, but you'd also be wrong. Because you're right in the common sense. You've never seen anything expand into nothing. But the universe just expands. It doesn't need empty space to expand into. Now, you don't believe that, do you? You do. Anyway, Google expanding universe and says, or write the question, what does the universe expand into? And then you'll see a long, 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 long explanation about it doesn't need something to expand into. It's very much like the question, what happened before the Big Bang? And I'll be talking a little bit about that. So, just keep in your mind that the universe is not a bomb blowing up in some direction. Okay, so here is some of the data that Hubble put together. Hubble was that astronomer. And so what he did, on the x-axis he plotted distance, on the y-axis he plotted velocity, and you can see that the further away you are, the higher your velocity. And that plot shows that the universe is expanding. The further away the galaxy is, so this galaxy is moving away like this, that galaxy is moving even faster. The further away, the faster it's moving away. But here's the weird thing. The galaxies are not moving. The galaxies are just like, picture this auditorium. You're a galaxy, you're a galaxy, you're a galaxy. And then what we're going to do is stretch the floor like a trampoline. Then all of you are going to move away from each other in every direction. Everybody moves away. But you're not moving. You're sitting in your chair. You're all sitting in your chair. All of these galaxies are sitting still locally, but because the entire fabric of space is expanding, the whole thing, you are all moving away from each other. And you will all see this redshift. Question? By the way, this data was in 1929. This square here is as big as that green square. So in the last 80 years, we've made a lot of progress by looking at ever more distant galaxies and found this line goes on and on and on. The universe is expanding and expanding. Okay, so the one fact you need to know about the universe, if nothing else, the universe is expanding. As it expands, it cools down. So here's time. Here's the radius of the universe. So that's just the distance between any two galaxies. Here's a galaxy, here's a galaxy. Let's just say that's 1. Tomorrow, they'll be like this. The next day, they're like this. The next day, like that. And that's what's plotted here, the radius of the universe. As the universe expands, it cools down. Just like the gas in a scuba gear. Has anybody gone scuba diving here? Who's a scuba diver here? Anybody go scuba diving? Somebody. Nobody goes scuba diving? You go snorkel? Oh, you go scuba diving. Okay. You have a tank, right? When you let air out of that tank, it gets cold, doesn't it? Matter of fact, the valve gets really, really cold. That's because it's under high pressure, and the air expands, it cools. The same thing is happening to the universe. As it expands, it cools. And here's the temperature of the universe, which is the temperature of the cosmic microwave background. I'll say that word again. Cosmic microwave background. Now, excuse me, that's what I studied. I did a PhD studying the cosmic microwave background. We call it the CMB. And we measured the temperature of the CMB, and the temperature of the universe is about 3 degrees Kelvin. Do you guys know the difference between Kelvin and centigrade? You do. So, centigrade is 0 is when water freezes, but that's 273 degrees Kelvin. And 0 degrees Kelvin is minus 273 degrees Celsius. So, the universe is expanding. As it expands, the photons in the universe cool down. Here's a picture of the universe expanding. And notice that there's black space around it, and it's expanding into this black space. It's wrong. It's a bad picture. But no one has successfully been able to make a picture of the universe expanding into something, because it doesn't expand into something. No, it's a difficult concept. But in any case, the universe here is like a ring, right? The universe, instead of being three-dimensional space, it's a ring right here. And then that ring gets bigger and bigger and bigger. Actually, it's a disk, isn't it? The universe is a disk here. That disk is getting bigger and bigger and bigger. And then through time, it gets that big. So we've reduced space to a disk, two-dimensional space. Now, one of the other weird things about the Big Bang was it was not an explosion. The Big Bang is our current best understanding of the origin of the universe, and it happened 13.8 billion years ago. Now the Earth is 4.65 billion years old. You know billion? 10 to the 9 years, billion, 1,000 million. How old is do we have any geologists around here? Are there any geologists? No. So anybody know how old the rocks on the surface of the Earth are around here? Are they 100 million years old or 200 million years old? Anybody know anything about the rocks around here? No. Okay, anyway, the rocks I would guess are, let's say 50 or 60 million years old. The Earth is 4.56 billion years old and the universe is 13.8. The Big Bang was not an explosion because it didn't happen. If it were an explosion, it would happen over there or over there. Where was the Big Bang? Where did this explosion blow off? Where did the bomb go off? And the answer is the bomb went off everywhere. It went off in this room. It went off outside. It went off 1 trillion light years in that direction. The universe was much smaller then, but it didn't explode. When you explode, a bomb has to have high pressure here and low pressure here. But our understanding of the universe is that we had the same pressure everywhere. As a matter of fact, if you have high pressure makes the universe contract, not expand. What makes the universe expand is not high pressure here and low pressure here. That would be your question about what did it expand into? You're used to having high pressure, low pressure, boom, bomb. That's not what the Big Bang was. The Big Bang was pressure the same everywhere and expansion. Now, you might say, how do you know that? Actually, look at that picture. That picture has a center, this picture has a center, this picture has a center. These are artists, they're all wrong. The Big Bang did not have a center. You cannot point to that direction. The Big Bang was over there. The Big Bang was over there. No, it was everywhere. In every direction you point, you're pointing to the past in the Big Bang. So, here's an observer, and if you look in this direction, you'll see a star. You look further away, you'll see galaxies. You look further away in that direction, you'll see faint galaxies, as I showed you in one of the earlier pictures. If you look further away, you see the photosphere of the universe. And that's what I studied for my PhD at Berkeley. We did an analysis of the photosphere of the universe. And the universe has a photosphere, and we measured its temperature to be 2.7 degrees Kelvin, very cold. And what we found were fluctuations in temperature of the cosmic microwave background. If you could see beyond that photosphere, you could see the neutrinosphere. And if you could see beyond that, you'd see the gravitosphere. And that would be, we don't have instruments to be able to do that. But we do have instruments to see the photosphere of the universe. Now, let me give you an idea of what that's like. Imagine if you're on a soccer field, football field, that goes on forever. There's grass everywhere. And you're standing there, just like you're sitting here, but you're standing on a field, and everybody is screaming. Ah! Everybody's screaming. Then you look at your watch, and you stop screaming. Okay? You stop screaming. Everybody stops screaming at the same time. What will you hear? Well, the first thing you'll do is, now light travels at about 330 meters per second. So after 1 second, nobody within 330 meters will be screaming. But beyond that, you will still hear them screaming. Because it takes sound a while. It takes longer than a second. If I'm at 400 meters, there's a guy over there. He's screaming, he stopped, but his scream is still coming. And so, essentially, you will be surrounded by what's called the surface of last screaming. So all these people have stopped screaming. Everybody has stopped screaming, but the time for those screams to get to you is finite. So after a second, you'll still be hearing this. After 2 seconds, you'll be hearing these people scream. After 3 seconds, these people will be screaming. Is that clear? It's called the surface of last screaming. What you're doing is you're listening back into time. Yes, does this make sense? Some sense? So the surface of, so a little bit of sense. Not too much. Okay. Well, if it doesn't make a lot of sense, ask your question, please. And then blame yourself if you don't understand, because I'm willing to answer your question. Does this make sense? The surface of glass screening. Why this is important is because we're going to replace the screens with light. Sound travels at 330 meters per second. Light travels at 300,000 kilometers per second. A lot faster. But it's the same principle. When we look as far away as we can see, we're looking back in time. Just like when you hear things from far away, you're hearing things from 1 second ago, 2 seconds ago, 3 seconds ago. Did you ever go to a track meet? And they have the man with the gun. There's a bunch of racers, 1, 2, 3, 4, 5. And the guy stands right here. He stands here, so all of these people, maybe he stands over here. He stands over here, very near, in the middle, so they all can hear the sound arrive at the same time. I remember when I was in high school, we had races, and let's say a 200-meter race. So we're all over here, and they had the guy starting the gun over there. And so he would fire the gun, and we'd wait and wait and wait, and then we'd hear it, and then we'd start running. And so we all had slow times. But then they put smoke in the gun. And so they'd fire the gun, and you could see the smoke, and you'd start as soon as you saw the smoke, because light travels faster than sound. In any case, we are surrounded by the surface of glass scattering from the Big Bang, just like the surface of glass screening. Now, when we look, we made a full sky map with the most sophisticated equipment. This is the COBE satellite. It was launched in 1989. We looked back at frequencies that we knew we could see this stuff, and this is the map we made. It's a beautiful map. Beautiful map. Matter of fact, well, this is the map of the cosmic microwave background radiation, and it's one temperature. It's 2.725 Kelvin. And that's one instrument on board the satellite. The other instrument made this map. This was what I worked on as a PhD. Now this is the galaxy, but these cold spots and hot spots and cold spots and hot spots, this was structure in the Big Bang. This is kind of like a baby picture of the universe. What you have to do is ignore the galaxy. The galaxy is just contamination. And look at these cold spots and hot spots. And John Mather got the Nobel Prize in 2006 for making this map. And George Smoot, my PhD advisor, got the Nobel Prize for this map that we made. And, well, you can see, ours map is better than theirs. Actually, this is a map of the temperature. It's a spectrum, really. But in any case, so here's a picture of me in 1992. That's like how many years ago? Like 18, 19 years ago. There's me in the office, and we're talking about a plot that was in the paper that he got the Nobel Prize for. I also said we got the Nobel Prize. So, how big is the universe? How big is the universe? Now, how big is the ocean? When you go out, has anybody gone on the ocean and lost sight of land? Has anybody done that? You have. Now, if you have a very, very accurate way of measuring the horizon, you can determine how big the Earth is. So, for example, if you have a ruler and you look at the horizon, if the horizon is perfectly straight, then the Earth is infinite. And if it curves a little bit, then that tells you that the Earth is not perfectly straight because it's a sphere. Now, I've been told by some people who travel in planes that when you get high enough, you can see the curvature of the Earth. Now, I've looked through this curvature, and I haven't seen it yet. But maybe my eyeballs are not accurate. Maybe I need a ruler, and maybe the portholes are too small or something. But it's very difficult to measure. But in principle, you can see that you can measure how big the Earth is by how flat that horizon is. And I'm mentioning this because that is how we measure the size of the universe. And the answer is, it is as flat as we can measure. That means that the universe is consistent with being infinite. Now, what do we mean by that? Let's explain a little bit. How do we measure the size of the universe? If the universe were shaped like the surface of the Earth, if it had a closed spherical geometry, then if we had a distance d, it would subtend an angle here. Now, if we are in this type of universe, an open geometry, then the same distance would be a smaller angle. This angle is smaller than that angle. If it's flat, then we have an angle that's somewhere in between this angle and that angle. So if we have a ruler, a standard ruler of length d, we put it at a distance, we say, okay, here and here, what's the angle? We can measure the geometry of the universe and determine whether the universe is finite, or infinite and open, or infinite and flat. And that's what we do with the cosmic microwave background. And here's some details about it. Here's the map of the sky. It's a new satellite, not the COBE, but the WMAP satellite. This is what's called the power spectrum. You don't need to know the details. Basically, see, this is 2 degrees, it's half a degree. About 1 degree, there's this peak that we measure the angle of, and we get this, that it's perfectly flat. That's what this, just a parameter, omega k. When it's 0, it means it's flat, and you can see that all the evidence is consistent with the universe being spatially flat, which means that the data tell us that the universe is spatially infinite, goes on forever. I don't know if you know this, that you live in an infinite universe. That has a lot of profound philosophical implications. For example, what is your name? What? Ura. Now, if the universe is infinite, and the probability of Ura existing is some small number, epsilon, 10 to the minus 127. If I multiply a small number, epsilon, times infinity, we have a math major here? We multiply epsilon times infinity, what's the answer? Infinity. Good, we have a mathematician here. So you multiply epsilon times infinity, you get infinity. So that means that there's an infinite number of mura. There are an infinite number of muras in the universe. An infinite number of muras in the universe. That's kind of weird. But that depends on his probability. I think the probability of mura might be 0. I'm not quite sure what the probability of you being here is, but most people think this is tiny probability. And if you say it's tiny, well, I just multiply it by infinity, and I get an infinite number of muras. So that's one of the weirdnesses of living in an infinite universe, that anything that has a finite probability exists an infinite number of times. You guys think that's crazy? You think that's weird? It might be true. I should say one caveat. I said, to the extent that we can measure, it looks flat. But our measurements are not perfect. So we cannot say that it's perfectly flat. And so it might be finite, it might be closed, but it's very big. And we can't tell the difference between a very big but finite universe and an infinite universe. Yes, the error bars are getting smaller and smaller and smaller, and that means this universe is getting bigger and bigger, but it's consistent with being infinite. And you can see the size here. For example, there it's 0, it's right in the middle there, but it's not exactly 0. No scientific measurement is exact. Here's another way to understand that. We have 2 parameters. Here's the omega matter, that means how much matter is in the universe. And here's this cosmological constant that you asked about earlier. And when we measure where this value, and we measure that value, we get a value that's right there. Matter of fact, do I have a green dot? Yes. That's how accurately we can measure these 2 parameters. And that tells us that the universe is flat and infinite. And it's accelerating up here. Ooh, everything up here is accelerating, everything here is decelerating. So if it were here, it would be finite, like a sphere, like this. So this shape is all here. This shape is right this line here. And this shape is all of this area. And you can see that the dot is consistent with being flat, but there's a little bit of slop here on both sides of that line. Any questions? So anyway, I'd like you to think about the idea of the universe being spatially infinite and what that means. All right, so where is the universe? Now here's another weird idea, and that is that it could be that there are many other universes. Now what do I mean by that? Well, when we study the Big Bang, we use quantum mechanics. We use quantum cosmology to do that. And quantum mechanics is a science that talks about statistics and probability. It doesn't say it must do this. There is not a unique understanding of the Big Bang. Rather, our mathematics suggests that there were many Big Bangs. And that's what these are. Here's our universe. Well, actually, here's our galaxy. And here's the observable part of our galaxy. And when I say that, I say observable, notice that it's a circle here. I can't see forever because the speed of light is finite. 300,000 kilometers per second is not infinity. If the speed of light were infinite, I could see forever in 13.8 billion years, the age of the universe. But I can't. The speed of light goes 300,000 kilometers per second. So in 13.8 billion years, it can only travel a finite distance, and that's what that distance is here. That's the radius of our observable universe. That does not mean that the universe stops there, but it does mean that we cannot see beyond here because the universe isn't old enough. Why? Because when you look back away, you're looking back in time. A telescope is a time machine, right? When you look at the moon, you're not seeing the moon as it is now. You're seeing the moon as it was 1 second ago. When you look at the nearest star, you are looking at that star 4 light years away. You're looking 4 years into the past. When you look at the nearest galaxy, Andromeda, which you can see from the northern hemisphere, it's the most distant object you can see with your naked eye. It's called the Andromeda Galaxy, and maybe you know something about the mythology of Andromeda. But anyway, it's 2 million light years away. So when you see light coming from Andromeda, you are looking at light that left Andromeda before there were human beings on this planet. Humans are about 100,000 or 200,000 years old. So you're looking at light that's older than humanity. In any case, there may be an infinite number of infinite universes. We're not sure about this, but that too is consistent with our understanding of the universe. I forgot to say, here's our observable universe, here's the entire universe here, and here's a baby universe, here's our mother universe, our brother universe, etc. This is something called eternal inflation. It's one model that cosmologists are playing with to try to understand the Big Bang. But I want to point out that the great thing about cosmology is on the largest scales will always be lost. As a matter of fact, that's been true of humanity forever. On the largest scales, we don't know where we are. The people at Çatalhöyük, 6,500 BC, they had a vision of the world where they knew about the near, but you know what? 100 kilometers in that direction, there were just dragons and crazy people of other different tribes who would eat them up. And so on the largest scales, they were lost. Today, that remains true. On the largest scales, we're lost. We don't know whether this picture is true or not. It's very hard to verify this type of idea. But it is one idea that we should keep in mind. But just because we don't know exactly, that's all right. That's what science is about. Not knowing for sure and trying to test the idea as best we can. So does anybody think I'm crazy for saying this? You guys believe this? Can you entertain in your mind, there might be other universes? And people say, yeah, you're crazy. But I'm telling you that when we do research in cosmology, this is one of the ideas that is still plausible. It's still reasonable. As a matter of fact, some people think it's more reasonable than thinking that there is only one universe. And then you would say, if you're a linguist, wait a minute, universe one, it means there only can be one. Well, this is the progress of science. We have a theory. Our best understanding of the origin of our universe doesn't suggest indirectly that there are other universes. So it's not a crazy idea. That's the best idea we have. But it's not very certain, and so we have to test it. And don't ask me how we're going to test it. we don't know. All right, I wanted to say, I have a few minutes left, and this is a telescope. It is the largest telescope in Australia. It was made to make this map. And here's the map it made. And every single dot there is a galaxy. So it's kind of like looking in this direction, and looking in this direction, and getting the distances to the galaxies, and then plotting it. And you can see that if the galaxies were random, this is what it would look like. But they're not random. And so the question is, why aren't they random? Where did the pattern come from that created those bubbles? They're kind of bubbles there in walls. And where did these walls and voids come from? Now here's a weird idea that I wanted to run past you. Here is our best understanding of how that structure got there. You take bubbling froth of universes, you blow it up during inflation, so the tiniest fluctuations on 10 to the minus 33, you blow up to the largest scale structure, and then you see it right here, the hot spots and cold spots. So simultaneously, that spot right there, or this spot here, is the largest structure in the universe, but it also came from the smallest structure in the universe. That's what inflation does. Another Zen-like craziness that cosmology, you can see that why I study cosmology. It's full of crazy ideas that are our best understanding of the universe. So for example, you say, the universe used to be as big as a grapefruit, and then it expanded. But what I'm telling you is that grapefruit, that small observable universe, 13.8 billion years ago, there's a grapefruit over there, and the same grapefruit is over there, as far as you can see. Now that sounds crazy. How can you have a grapefruit over there and a grapefruit over here? Well, you have to study a little bit more, but I guarantee you that you can understand it. Now, how did the universe begin? Here's the Big Bang. Here are what we call quantum fluctuations. Here is the map that we made of the universe, the Photosphere Universe. And here we are today. When we discovered this in 1992, the universe was about 15 billion years old. Now it's 13.8 plus or minus 0.1. That's the age of the universe. We get that from looking at these fluctuations, and we think that there were quantum fluctuations here that produced those seeds. And I'm running out of time, but you might say, well, what happened before the Big Bang? And this is a diagram of why that question does not make sense. If you do science, you make plots like this, space and time, and you're used to that. But gravity bends space and time. It can not only make it expand or contract, it also bends it. As you get closer and closer to the Big Bang, you get the bending of space and time. So this space goes, and then if you go early enough, space and time turns into space-time foam, which is why you cannot go earlier than the Big Bang, because you end up going all over the place. You have a space-time foam. And that's why you cannot ask the question, what happened before the Big Bang? Because the question, you're assuming time goes on. You're just assuming linear time. Well, time stops being linear and turns into space-time foam. Any questions about space-time foam? Okay, let's see. Here's a beautiful image of what we think the Big Bang looked like. Matter of fact, this might be our universe, and then it came out, but there are other universes popping out of this space-time foam. And how about the age of the universe? Say, how do we know the ages? Well, this is Bishop Ussher, and he calculated the age of the universe. He used the Bible. Somebody begat, somebody begat, somebody begat. And he got 4,000 years BC, and you add on this today, and then you get the universe is 6,015 years old. And most scientists laugh at this, but I should say, you shouldn't laugh at this guy, because he was using the best scientific data at the time, and that was the documents available. He didn't know about carbon dating, radioactive dating of rocks, etc. He just had begats. And that gave this date. Now, we know that this is wrong today because we have better data. Here's a plot of the ages of different things. You can ask, maybe later you can ask me, but the sun is this big, the sun of the earth is this old, the disk of our galaxy is this old, the galaxy halo, and then the universe is, actually look at that. I got this date about 10 years ago, but it has improved since then. And here is some of the reasons. I wanted to give you some of the reasons of how we know this age, but I don't have time. There are about 10 different ways to do this. And some of them complicated, some of them simple. And what is the universe made of? Well, here's a plot of our best understanding of what the universe is made of. Now, if you look around you and you feel yourself, you are made out of baryons. You're made out of carbon, hydrogen, nitrogen. Matter of fact, here's what you're made of. Life is made of this much hydrogen, oxygen, carbon, and nitrogen, and then sulfur and phosphorus. At the 99% level, that's what you're made of. You go like, everything you're thinking with your eyeballs, the plants outside, the fungus, the bacteria, everything, life forms are made like this. And the sun is made out of mostly hydrogen and helium, and 1.5%, this number has changed, 1.5% other stuff. The universe is a little different. The universe is made out of 75% vacuum energy. So most of the universe is made out of nothing. That's another name for vacuum energy. Or, as you point out, cosmological constant. We have discovered this in the last 10 years. So this is in the last 10 years, this plot is only about 10 years old. About a quarter of it is made out of cold, dark matter that gravitates, pulls things together. This stuff makes the universe accelerate, expand even more than it already is. And then 4.4% of normal matter. And that's what the universe is made of. And if you want to know how we know that, well, you're going to have to study some more cosmology. But you can see the difference between the sun is made out of this stuff, and then life is made out of these elements that are made out of some small contribution in the sun. Here's a logarithmic plot of that. So hydrogen, helium, and then carbon, oxygen, nitrogen. Notice that the life is made out of H, O, C, and N. Life is made out of the most abundant elements in the universe. You're not made out of something special. You're made out of the most abundant ingredients in the universe. You're like a piece of bread in a bakery, and you're surrounded by flour. No wonder I'm made out of flour. There's flour everywhere. That's what life is made of. You're not made out of lead or bismuth or samarium or europium. You're made out of the most abundant stuff in the universe. Here's a picture of the periodic table. If you've had chemistry, you learned this. And the universe, the sun is made out of that. Hydrogen, helium, and then this other stuff. Here's a picture of the ingredients of the sun. Hydrogen, this much. Helium, this much. Oxygen, this much. Carbon, then neon, then nitrogen. And if you take away the noble gases, take away helium, take away neon, you're left with what life is made of. Life is molecular. So, in this lecture, I've tried to answer 5 questions. What is a universe? The universe has changed over time as we learn more and more about it. How big is the universe? It looks like the universe is spatially infinite. And there are an infinite number of U's in the universe, if the probability is not 0. How did the universe begin? We talked about space-time foam and quantum cosmology. A statistical description which suggests the existence of other universes. How old is the universe? 13.8 billion years, plus or minus 0.1 billion. And what is the universe made of? It's made out of vacuum energy. It's made out of the cosmological constant is another name for that. And it's made out of about 25% dark matter, also something we don't know that much about. And only 4.4% of the universe is made out of baryons. So, I'll be here for a few more days. If you have any questions, I'd be happy to talk to you about them. And I'll be giving a lecture to this class on Wednesday, right? About Darwinism. So, if you have any questions, please come up. Thank you very much.